A very widely used application and very important problem in linear algebra is known as the eigenvalue problem. This is covered in Greenberg's chapter 11.1 and 11.2, and it's defined basically as this equation: ax is equal to a scalar quantity lambda times x. And you might recognize this, it's a special case of the system ax equals c, which we've talked about quite a bit. After taking careful notes in this video and in working through your problem set, you will have the ability to recognize whether a vector x is in fact an eigenvector of matrix A, and if so, explain the meaning of the eigenvalue lambda. You'll be able to solve the eigenvalue problem mathematically, and then you'll also be able to apply the solution to solving to a couple of example applications. One is solving a system of coupled ODEs, and the second is a Markov process. So just to remind you, we've talked in length about the system or the equation AX equals C. And one interpretation is that AX transforms, or I should say just A, I guess, the matrix A transforms vector X into a new vector C, generally having a different magnitude and length, sorry, a different magnitude and direction from X. So that's a relatively simple interpretation of this. We have a vector X, and when we multiply it by A, that vector is transformed into this new vector C. Now the eigenvalue problem is a special case. It's a special case of AX equals C, and is stated, the statement of the problem is A x equals lambda x. And here lambda is a scalar. And so for this special case, x is, so let's see, in this special case, A only changes the length of x, length or magnitude of x, not its direction. So this is a special case. And this can only happen, this is only possible for some specific vectors. And those vectors are the eigenvectors. Eigenvectors. So only for the eigenvectors of matrix A will operating A on those vectors only change its magnitude and not its direction. And so lambda is just controls how the magnitude changes, and it's called the eigenvalue of vector x. And I also want to point out that the eigenvectors and their associated eigenvalues are properties of A. So again, for this to be true, the eigenvectors and eigenvalues reflect intrinsic properties to the matrix A. And therefore, the eigenvalue problem is to solve for these properties. That is x and lambda. Okay, so that's a statement of the eigenvalue problem. Given ax equals lambda x, solve for lambda and solve for x. So I'm going to summarize the solution, the method. Summarize the solution method to the eigenvalue problem. So again, we start with ax equals lambda x, and we can reformulate it the equation as follows. We're going to change it into a new matrix equation. So again, we have ax on the left-hand side, and we can multiply the right-hand side by the identity matrix, because the identity matrix times any vector will equal the same vector. So this is true. And then when we do that, we can bring the lambdas and the x. Well, we can subtract the right-hand side from the left-hand side, and we get this. And what we've created is a new matrix equation, where the new matrix, we'll just call that A prime. That's equal to A minus I times lambda, where I is again a diagonal matrix. So we're just going to subtract lambdas from the diagonal elements of A. And that gives this new matrix AX, or A prime. And the new equation is A prime X is equal to 0. So again, our aim is to solve for lambda and x. So that's the goal of this problem. Now recall that an equation of the form of ax is equals to 0 always has a solution. And it includes the trivial solution, x is equal to 0, the zero vector. Okay, so we can always solve that system, but we're not interested in the trivial system. We want the non-trivial solution. Or really non-trivial solutions, because the solutions will be plural in general. And they exist. So the non-trivial solutions to ax equals 0 exists only if A prime has linearly dependent rows. Okay, and we've talked about this before, but let me remind you why. Because remember, a prime x can be represented as a linear combination of the columns of A, not rows, the columns of A. So column 1 times the first element of vector x plus column 2 times the second element of vector x added progressively all the way out to column n times the nth element of vector x. So this is a restatement of this equation. Right? And if this is true for the non-trivial case, that is when all the x's, oops, this should be x2. When all the elements of x are non-zero, this requires that the columns are linearly dependent. In other words, we can add these vectors or multiples of these vectors, and the only way to get 0 or get back to the origin is if the columns are linearly dependent on each other. And so, and if the, let's see, I stated here they exist only if A prime has linearly dependent rows and columns. I should add that. Because any matrix that has linearly dependent columns also has linearly dependent rows. And for this to be true, if the rank R is less than n, the dimension of the matrix A. And I should mention that here that I forgot to mention that A is a square matrix. It's n by n. Okay, so a square matrix with linearly dependent columns has a rank that's less than n. And therefore, the determinant of A prime is equal to 0. So to solve for the lambdas, right, which are in the diagonals of A prime, we have the strategy is then to set the determinant of A prime equal to 0 and then solve for the lambdas. So we set the determinant of A prime, which again is A minus the identity matrix times L, equal to 0, and solve for lambda that makes this true. We solve for the lambdas that make this matrix have linearly dependent columns. So this becomes our characteristic equation. It is an n order, or I'm sorry, an n degree polynomial It's simply a polynomial. A determinant of this form is an n degree polynomial of lambda, and thus lambda will have n roots, that is n possible solutions. And each root for lambda will have an associated eigenvector. So we've solved, once we find our lambda roots, now we have to solve for our, once we've solved for our n roots of lambda, our eigenvalues, we now have to solve for the eigenvectors associated with those eigenvalues. So we solve for x by solving our original equation. Well, not our original equation, I guess our modified equation, which was a minus I lambda x is equal to 0, or a prime x is equal to 0. And we already know how to solve this type of equation, and we solve it using Gauss-Jordan reduction, or Gauss elimination, or Gauss-Jordan reduction. And you should also note that we cannot solve it using the inverse or Cramer's rule. We can't do that. And maybe you should ask why, and I hope you do. But the answer is, the reason we can't solve it using the inverse or Cramer's rule, because again, the determinant of A prime is equal to 0. And so any matrix with a 0 determinant doesn't have an inverse. And again, Cramer's rule was inversely proportional to the determinant, so we can't use that either. And related to the fact that the determinant is 0, and remember, A prime has a rank R less than n, related to that is that it has a nullity. We've used that term before. Its nullity is P is equal to n minus R. And thus, I guess the solutions for x are non-unique. This system has a P parameter family of solutions. Right? So in other words, the eigenvectors can have any length, any magnitude, an infinite number of magnitudes. But that said, there are only less than or equal to n different directions for the eigenvectors. So in general, there'll be n different eigenvectors, and there may be n distinct directions for those eigenvalues, but there's also the possibility of 2 or more eigenvectors having the same direction. So I've outlined basically a two-step process for solving the eigenvalue problem. The first process was to set the determinant of the modified matrix A minus I lambda equal to 0 and solve for the lambdas using the characteristic equation. And then the second step was for each solution for lambda, uh, solve for the associated eigenvectors by substituting that lambda back into the equation and solving for x using Gauss elimination or Gauss-Jordan reduction. So 2 steps. And so that's how you do it. Next, let's look at an example. In this example, A will be a 3 by 3 matrix. 2, 2, 1 on the first row, 1, 3, 1 on the second, and then 1, 2, 2 on the third row. And remember, the goal is to solve for lambda and x in the equation, in the eigenvalue equation, Ax is equal to lambda x. And the first step is to solve for lambda, and we do that by setting the determinant of A minus lambda times the identity matrix equal to 0. And the determinant of A minus lambda times the identity matrix is the determinant of 2 minus lambda in the upper left diagonal, followed by 2 and 1. And then we have 1 times 3 minus lambda, and followed by 1, and then 1, 2, and then 2 minus lambda in the lower right-hand diagonal element. And this gives the characteristic equation of 2 minus lambda times 3 minus lambda times 2 minus lambda minus, oh, I'm sorry. Yeah, that's correct. 2 minus lambda times that, and then minus 2. And then we have a minus 2, which is this element, and we have to cross this row out and that column out, and we get a 2 minus lambda minus a 1. And then we have a plus 1 times 2 minus 3 minus lambda. And that gives the equation of lambda minus 5 times lambda minus 1 squared. So that's, again, it's a third order polynomial. And when we write the polynomial like this, we see that lambda is equal to 5 and 1. And we should have 3 different roots. So the second root, lambda 2, which is equal to 1, is repeated. It's repeated. We know the second root is repeated because we have lambda minus 1 multiplied by lambda minus 1. So the second root is repeated and has what we would call multiplicity of 2. So we have 3 roots, 5, 1, and 1. So for lambda 1 equals 5, let's solve for the eigenvector. Eigenvector or eigenvectors. And so A minus lambda 1 x, A minus lambda I x equals 0 means or that can be rewritten as minus 3, 2, 1, 1 minus 2, 1, and then 1, 2 minus 3, x1, x2, x3 is equal to 0. And so we can write this in the augmented matrix form. And this gives the, and reduced by Gaussian elimination, and we get 1 minus 2/3 minus 1/3, 0 in the first row, 0, 1, minus 1, 0 in the second, and then we get all zeros in the bottom. And so we find that n minus r, so that is equal to 3 minus 2. Our rank is 2 because we have 2 columns left after we've done our Gauss elimination. And so we have one parameter. We have a one parameter family of solutions. And so that'll be x is equal to alpha. x3 is equal to alpha. With x2 equaling alpha, because the second equation is x2 minus x3 is equal to 0. And then finally, x1 using the first equation is equal to 2/3 plus 1/3 alpha, and that's equal to alpha. So the eigenvector the first eigenvector is, we'll denote that as E, I is equal to alpha times 1 times the vector 1, 1, 1. So it's a vector of any length oriented in the 1, 1, 1 direction. And so the eigenspace of lambda 1 is equal to 5 is the span of 1, 1, 1 transpose. So it's the span of that one vector. And this is a 1D subspace of 3D space. And Greenberg denotes 3D space as capital R. It's kind of a fancy R, 3. So this is a one-dimensional eigenspace corresponding to the first eigenvalue. The second eigenvalues were lambda is equal to 1 and 1. So I guess that's lambda 1 and, lambda 2 and lambda 3 is equal to 1 and 1. And so our equation A minus lambda I x equals 0 is written in matrix form as I guess the augmented matrix A, and then C is 1, 2, 1, 0, 1, 2, 1, 0, and then 1, 2, 1, 0. And this is reduced with Gauss elimination, and you can see that we would have only one independent row. So the rank here is only 1, and P is equal to N minus R is equal to 2. So we have 2 parameters that describe the eigenspace. And so this is x3 is equal to, say, beta, and x2 is equal to gamma. And the first equation states that x1 is equal to minus 2 gamma minus beta. And so the eigenvector for these eigenvalues so the 2 eigenvalues vectors are equal here, is equal to beta times minus 1, 0, 1, right? So this is minus beta for the first part, which is x1, and then beta for the third part for x3, and then we have plus gamma times minus 2, and x2 is a 1 times a gamma, and x3 is a 0 times a gamma. So this is the eigenvector. These are the eigenvectors for the second and third eigenvalues. And so we would say that the eigenspace of lambda 2 and lambda 3, which is equal to 1, is the span of the 2 vectors minus 1, 0, 1 transpose, if we describe a vector as being a column vector, and minus 2, 1, 0 transpose. And this is a 2D subspace which is a plane of 3D space, again R3. So the second, third eigenvalues, second, third eigenvectors lie in a plane. So our solutions for the eigenvectors are this, our eigenvalues are that, and we also have the first eigenvalue and the corresponding eigenvector. And that is how to solve the eigenvalue problem.